speaker of the night. It's Computational Imaging Lab. He got his bachelor's and master's over at Brigham Young, and he's done some work on satellite remote imaging, and is interested in new computational algorithms, which he's going to be talking about tonight. Non-line of sight imaging, single-photon imaging, as well as 3D imaging with sensor fusion. So please give a warm welcome for David.
Thanks for the introduction and for the invitation to come and speak tonight. I think some of you may remember one of my lab mates, Nitish, came and gave a talk about some of his work in AR, VR. And generally in the lab we have a few different areas that we're working in, and what I've been working on is more related to 3D imaging and LIDAR, and we happen to be able to talk to you about some of the research projects that I've been involved with over the past few years. So I'd like to start off with this series of images of a horse in motion. These were captured in 1898 by a man named Edward Muybridge at Stanford, and he captured these to settle a bet that Leland Stanford had. And so Leland Stanford had this bet as to whether there's a moment in time where all four hoofs of the horse are off the ground together. And he captured this, was essentially a high-speed video or sequence of frames that he captured at the time. And if you look through them, you can see that actually, yeah, that does happen. All four hoofs come off the ground. So how did he capture this? It was much more limited in the technology that he had. And so the way this worked, he constructed this sort of virtual high-speed camera array. He had a bunch of cameras that he lined up, and the horse, as it moved through, would trigger these tripwires, which would then trigger these short mechanical shutters, short exposures of each camera, and you could capture maybe like a 20 or 30 frame per second sort of video here. And actually, for those of you who are familiar with the Matrix, they actually captured those bullet time animations in a very similar way, this sort of camera array. So this is a very early type of computational imaging. You could think of it done at Stanford, where you're designing hardware for very specific imaging tasks, and some of the work that we do in the lab I think of as continuing on this legacy of computational imaging, both combining hardware and now computational algorithms to do new and exciting types of imaging. So of course nowadays we have much more sophisticated sensors, and in this talk I'll be talking about these 3D imaging devices called LIDAR, and we're imaging actually things that move much quicker than horses. So in this case we're actually imaging light and measuring how long it takes for light to travel to a point and return, and then based on that speed of light time delay we can actually determine distance. So this is how LIDAR works, and you frequently see these sensors on the tops of self-driving cars, and the output that you get from these types of sensors looks something like this. So this is a 3D point cloud. You're basically capturing the 3D geometry of the surrounding scene by measuring a bunch of times how long it takes for light to travel to each point and return. So you actually captured one of these measurements for each 3D point, and you can basically see a 3D structure of different objects on the road, pedestrians and cars. And so, of course, these are really useful for self-driving vehicles, and I think we've all probably seen these in the area. Google or Waymo's self-driving cars. So this has a high-powered LIDAR system at the top, along with a whole suite of other sensors, radar, ultrasonics, conventional camera vision systems that they can use to see street signs, stoplights, and help the car navigate. There are actually a whole host of applications for LIDAR systems, and I'll just go through a few. So one would be remote sensing and aerial imaging, so we actually construct fairly detailed maps of vast tracts of land by putting these on a plane and flying over and scanning. So I think about a year ago, they used this type of technology to actually digitally remove the forest canopy and uncover ancient Mayan ruins and figure out where those buildings were and what they looked like. We use LIDAR on the International Space Station, so the the capsules that we send up to dock with the space station actually have LIDAR on them, and then they use this to determine the distance from the space station, their orientation, so that they can dock correctly. Of course, there are applications in surveillance and defense, and here are a few other interesting applications. 3D mapping. China's apparently developing a satellite-based LIDAR system that can track submarines that are hundreds of meters below the ocean surface. Applications tracking space debris in optical communications and quantum communications. Okay, but maybe something that's a little closer to home, and maybe some of you have this in your pockets. We're actually seeing more and more 3D imaging technologies deployed on smartphones. So this is the iPhone 10 from Apple, and it has a 3D imaging system. It doesn't work quite the same way as LIDAR does. In this case, it's a structured illumination procedure for recovering 3D structure. So they actually project these random dot patterns out, and then use those to determine the 3D geometry. So you wouldn't actually see the dots because this is projected out using infrared lighting, but the sensor can pick this up. And this is useful for, I think most people know this is used for the authentication systems, helping to make things a bit more secure. But actually they have a whole suite of sensors, and another one that I want to point out is this proximity sensor. So actually the iPhone 10 has, this is basically a single pixel LIDAR baked into this sensor bar here. And actually, well, here's another application of 3D imaging on a phone. The Huawei P30 Pro has a full 2D frame time-of-flight sensor. So they get a 2D depth map out of this sensor on the camera. So we're seeing these types of technologies being miniaturized, commercialized, incorporated into devices that we carry in our pockets and use every day. Now, the way LIDAR works is actually fairly simple. So we have some detector that can measure the time that photons are arriving, and we synchronize this with a laser that sends out short pulses of light. These are both focused onto some point in the scene, and the detector simply measures how long it takes for that pulse to travel to the object and then bounce back and travel back to the detector. And if we wanted to capture a 2D image of depth map or a 3D point cloud, we could simply scan this around the scene, or we could also use a 2D sensor and a flood illumination pattern to kind of do this all in parallel. So there are really three main challenges with these types of LIDAR-based 3D imaging systems. First would be light efficiency, how much signal you actually get back. Of course, you are actively illuminating something, so you have a finite number of photons that are going to travel to that point and come back. How quickly you can actually timestamp or localize in time those arriving photons. And then the types of algorithms and inverse problems you can apply to improve performance, improve accuracy, and perhaps even extend the maximum range that you can see things at. So I'll spend a bit of time on each of these just to get into a bit more detail. So if you take a laser and you point it at some distant scene point, the amount of photons that are going to come back falls off as 1 over the distance squared. This is actually a pretty rapid fall-off rate, especially if we're thinking about imaging objects a few hundred meters away, which we definitely want to do when we're putting LIDARs on self-driving cars. And so you would think that a quick fix for this would be to just turn up the laser power, but the fundamental limit on this is what you can actually, how much power you can emit safely, so that if the laser beam were to come across someone's eye, that you wouldn't blind them. In other words, this has to be eye safe. And so, and then you could also think about optimizing the other side at the detector, so that your detector is sensitive enough to capture every single photon, ideally, and then you'd have as much signal as possible. The second challenge was how quickly you can actually, or how accurately you can timestamp these incoming photons. So you have to do this fast because the speed of light is so fast. So light travels about 300 million meters per second. So in just a few nanoseconds, light is traveling a meter, and in a few picoseconds, it's going to travel around a millimeter. But picoseconds, these are just incredibly small timescales. So we need specialized hardware to do this, and there are sophisticated, they come in large boxes, custom electronics you can buy that do this, but increasingly we're seeing these types of time-stamping circuits integrated in ASICs and FPGAs, and so the form factors are becoming smaller. This is becoming miniaturized and more accessible as well. And finally, what types of algorithms can we apply for the inverse problem of estimating the depth from the measurements? So this is an example of a paper that came out about 5 years ago called First Photon Imaging. And what they had here was a LIDAR system, and you would scan this around, but you would only detect a single photon at every scan point. So incredibly low signal regime. And if you would apply some conventional method for estimating the depth, you would get some very noisy estimate. But if you were to come up with something a bit more clever, apply some computational algorithms, you can actually get a pretty good depth map, again, with just a single photon detected at each spatial location. So I think this example really motivates the power of these computational algorithms to improve the quality of the results that we can capture. And I think helps motivate research in this area and shows really what you can do. It makes this an exciting topic to work on for people like me. So we also have to decide what types of detectors we're going to use. And there are really, I would say, two main detectors that are being used. These are avalanche photodiodes, APDs, or single-photon avalanche diodes, or SPADs. You can think of APDs as a conventional photodiode, but with a really high amplification factor or gain. These have a slightly worse time resolution than SPADs, in the hundreds of picoseconds regime. And you need typically a few hundred photons that are actually hitting the sensor to get a detection. The other sensor, and this is the one that I've been focusing on, called a SPAD, the difference from an APD is that you're operating this in what's called Geiger mode. So you basically turned up the bias voltage on this photodiode so that you're in this unstable regime where even a single charge carrier that hits the surface of the sensor can trigger an avalanche of current. So in this case, the timing resolution becomes much better, typically a few tens of picoseconds, and because you have this sensitivity, you can actually detect down to the single charge carrier, or actually single photons that are coming onto the sensor. And so this has advantages, especially if you're trying to do ultra long range sensing or you really need good timing accuracy. So again, this is what I'll be talking about in this talk. So how does a SPAD work, and what types of measurements do we capture? So again, we pair our SPAD sensor with a picosecond laser. This is sending out very short pulses of light into the scene millions of times every second. And for each pulse that goes out into the scene and comes back to our sensor, we have a chance of detecting a single photon. And when that happens, the circuitry in the detector generates a timestamp of when that photon arrived with respect to when the laser pulse was emitted. And since we're doing this so rapidly, millions of times every second, we're sending out these pulses, we can quickly accumulate all these timestamps in a buffer, and then we can bin them into a histogram based on their time of arrival. So this histogram is just showing the number of detections over time, and you would expect the peak here to basically give you the time of flight, or basically the distance to that scene point. Now we can also, if we wanted to build up a scan line or a 2D image, we could scan across the scene, or we could have an array of SPAD detectors. So in this case, a line array would image a single scan line, and then for every sensor we get a histogram. And another way of visualizing this collection or array of histograms would just be in an image. And so we have a spatiotemporal image of where the vertical axis is indexing the pixels of our SPAD array. The time axis is again the time of flight of the photons arriving. And we can use these sensors to capture an image like this. So this is a regular image showing the scene that we captured. So we've got a fiber optic cable that glows when we send light through it. And we've hooked up to this cable a picosecond laser that's sending in these short pulses of light. And I can actually play these measurements back in time that we capture with the SPAD. And what you're seeing here is this pulse of light going through the fiber optic cable. And you can think of this as like a trillion frame per second video. We're actually able to visualize the light, pulse of light as it's moving. And you can even observe some interesting effects of how light is interacting and propagating through this fiber, interacting with the scene. So the light pulse actually broadens out as it travels through the fiber. You can see there at the end where it comes out, kind of splashes out of the fiber, and also see the reflections against the floor and the wall in the background too. So imaging at a trillion frames per second kind of uncovers this new dimension of scene understanding, and it's also just kind of fun to look at. Okay, so how do we capture this type of image? Well, in this case, we had a line array of SPAD pixels, and we scanned this array over the scene so that at every scan line, we're basically capturing one of these spatiotemporal images, right? This is just a 2D slice of a 3D volume. After we've scanned it over the scene, we have this 3D volume with two spatial dimensions and a time dimension. And then by just playing these time slices back, we've recovered this video, and we can see the light transport. So I'll show a few more results. This is a scene that has a Pepsi bottle. We filled it with water and then a bit of milk so that it would scatter the light out more so we can see the laser pulse. The right-hand image is the image that the SPAD captures, but just integrated over time, so kind of like a normal photograph. And of course, then we can play these time slices back again and then see the pulse going through the Pepsi bottle. So you can see it hit the cap, bounce back to the beginning, as well as see the light splashing it out on the floor and the wall in the background. Here's another scene. So we have the statue next to a wall, and then there's also a mirror. And the wavefront of light comes from the right, illuminates the statue, and then when it hits the mirror, you see it split in two, and then also see the reflected light go back the way it came from. So these data, these transient images are basically what we capture with SPADs or what we capture with the LIDAR system. Probably the most useful application of transient imaging data are for depth estimation, 3D imaging, LIDAR. I'll also be talking about an emerging application called non-line of sight imaging later in this talk. And in general, you can use this type of transient imaging data for just generally understanding light transport in a scene, separating light that directly bounces back to you versus light that's scattering a bunch of times in the scene. We could use it to image through scattering media like fog or murky water because we have this time resolution and can see how the light scatters through things. And this is an emerging imaging modality, and I think there are a lot of exciting applications that we have yet to uncover and still a hot topic of research. So I introduced transient imaging and talked about this a bit, and I want to go into some of these other applications, starting with 3D imaging and some work we did on 3D imaging at really low photon, single-photon levels. So I told you that this is probably the most important application of the transient imaging data. And one of the main challenges is that if you have a LiDAR system and you want to image very quickly, say you want to read out or scan the scene at 60 frames per second, well then you've got to scan every pixel, right? And if you want a high resolution image, you actually have very little time very little exposure time at each pixel, which means you actually are in this very noisy regime, you have very low signal, and so it can become actually very challenging to try to estimate the depth from these very noisy measurements. So on the left here is an example of measurements that we captured with our LiDAR system, and this is a conventional image of the scene. The white dots that you see in this 3D volume are the photons that are arriving over time, time being the depth dimension. And you can kind of see the structure of the scene, but that's mostly due to the ambient light. So we're getting photons arriving uniformly over time just from ambient light, and that allows us to kind of see the structure of the scene. But also embedded in this mass of photon detections are photons that came back from our laser. And we need to figure out when they arrived to be able to get the depth. So we have this interesting idea looking at these two sources of data, and they're clearly complementary in many ways. One is higher resolution, on the right is low noise, but doesn't have as much information potentially about the depth. On the right we have embedded in here information on the 3D structure of the scene. So the question is, can we combine these inputs to perhaps improve the depth estimation? So in this case we took a learning-based approach and designed this neural network architecture to do this. And there are a few different ways we can do this. So we can estimate depth using this neural network with just the SPAD measurements. And we can also pass in features from the intensity image to this neural network to try and improve the depth estimate. And finally, we can look at adding on a higher level task like trying to upsample this depth map using the higher resolution intensity image, and then training the network to do this end to end. So we trained this network, and we also built this hardware prototype to test this out on captured data. So this is a custom LiDAR system that we built. We have a picosecond laser that we have illuminating a vertical scan line, and then we have a 1D SPAD array that is imaging this scan line, and then we scan it back and forth across the scene. So here's an example of the system in action. If you scan it under the ambient lights, you can't really see it. The laser we had for this prototype was pretty low power, so the range was limited to a few meters. But if we dim the lights, we can actually see the scanning. This is also captured at 240 frames per second, so slow things down a little bit more so we can see the scanning. Okay, and here's an example of a scene that we captured scanning at 20 frames per second. An intensity image on the left, and then what we capture with the SPAD array on the right. And you can see that it's actually pretty noisy. So on average, across all the spatial positions, we're getting less than a single photon detected from the laser. And here's some reconstructions. So on the top, I'm showing here in the middle a conventional approach based on matched filtering, which largely fails, produces a pretty noisy result. On the top right is what would be a state-of-the-art approach for depth estimation from SPAD measurements. And on the bottom are the outputs of the neural network. So we can actually get a much cleaner result and also do some upsampling, which improves the density of the point cloud, though in this case we have some floating pixel artifacts that persist. But overall, we can actually improve upon the state-of-the-art methods with this learning-based approach, and using sensor fusion also adds some improvement. And so just to comment on why deep learning is useful here. I think for these tasks like sensor fusion, you have these two sources of input, but coming up with some sort of analytical formulation on how to combine these is pretty difficult. However, we can leverage neural network architectures and how we train these to actually have the network learn from the data how these sources of input are complementary, and learn this mapping from input to the output that we want. And this idea could also extend to other sensors, ultrasonics, radar, thermal cameras, and we could also, talked a little bit about upsampling, but we could also think about applying higher level tasks like classification or object detection as our final output, and then training the network to do that end to end all the way back from our raw sensor measurements, and in that way kind of remove the typical heuristics that we apply and learn this whole process and probably gain some performance improvements as well. So I also want to talk about the work that we've done on non-line of sight imaging and just introduce this problem and what this means. So this is a situation we have some camera system down here. There's an occluder that's blocking our view of some hidden scene that we want to image, but we don't have direct line of sight. So if we look at what the camera sees, really all we can observe is this wall. And we'd like to image these objects. But we can use a laser to illuminate the wall, and some of that light will reflect off the wall to the hidden objects, then come back to the wall, and then back to our camera. You can kind of see actually the light from the wall hitting the statue, and then some of that is actually bouncing back to the wall and back to our camera. And from these indirect measurements of the multiply scattered light, we'd like to reconstruct the 3D geometry of these hidden objects. And actually we can do this pretty well. Okay, so here's a diagram again of what we're trying to do. So conventional LIDAR system, of course, is line of sight using direct access and be able to scan this object directly. Of course, in our case, we can't do that. And so the light, what we're interested in is light that bounces to this wall, to the hidden object, back to the wall, and then back to the camera. And if you are doing this with a SPAD, these are the types of measurements that you'd expect. So this is a histogram of the number of photons that we detect over time. And I've arranged this so that time 0 is the time at which we're detecting photons that are hitting the wall. So of course we get a lot more photons from the wall than we would get from the hidden object. That's the peak that arrives a few nanoseconds later, just because as light is scattering out, we're actually losing quite a bit of signal. And this is also why SPADs are really helpful. They give us both the time resolution, but also the sensitivity to detect these very weak signals from the multiply scattered light. And you can think of this time delay as intuitively has information about where this hidden object is, right? This is basically giving us some notion of the distance of that hidden object from the wall. Here's an example of this happening real time. So this is me, I'm holding this exit sign, and we're illuminating and imaging some spot on this wall outside. Of course, there's the bright peak that we see from the direct light. Then also you see the smaller peak, and that corresponds to this exit sign that I'm moving back and forth. So as I get closer, that peak is closer in time and also higher in amplitude. Well, having one measurement just doesn't provide enough information for us to reconstruct the full 3D geometry. So what we do is we scan around or scan a patch on this wall. This introduces some spatial diversity to the measurements, and the measurements that we capture then would look like this. So this is a 3D data cube, the two spatial dimensions that we scan out of the wall, and then for every scan point, of course, we get this histogram over time, and the measurements would look something like this if viewed as a 3D volume. And we can describe these measurements with some math in this image formation model. So the measurements, which I'll call tau, are related to the hidden volume, which we parameterize as a voxelized volume, basically trying to estimate at each XYZ coordinate the amount of light that's reflected, or the brightness, or basically this is the albedo at each XYZ coordinate in volume. And then we have these two terms here, one of which describes the decay and the intensity of the light as it's scattering out or as it travels. And then this other term is a geometric term which relates the distance from the wall to a point in the hidden volume back to the wall to the time at which we would see a peak or photons arriving in our measurements. And just a footnote here is that we can actually image and illuminate different points, and I'll call this non-confocal. Basically what a LIDAR system would do. I'll call it confocal imaging. Well, this equation can be written as a linear system of equations, and where we have the measurements that we vectorize and a transport matrix which relates the unknown vectorized volume back to the measurements. And there are a few techniques that can solve this system. There's a back projection technique that provides an approximate solution. Takes about 10 minutes to run for a low resolution hidden volume. And then there are also direct iterative conversion techniques that would take much longer, more than an hour typically for some low resolution volume. But the problem is that if we want to really scale this up and image higher resolution volumes, this becomes a really, really big linear system. So in practice, for just a hidden volume of 100 by 100 by 100 elements, A is going to have already a trillion elements. So you can see that this just isn't practical, or doesn't scale for higher resolutions. So the approach that we took was to take another look at this image formation model, and we realized that if we were to limit ourselves to just imaging and illuminating the same point, like the LIDAR system does, and scanning the same image and illuminated points along the wall, that this would allow us to perform a change of variables in this image formation model. I won't get too much into the details here, but suffice it to say that after this change of variables, we can actually rewrite this as not a full matrix multiplication, but a convolution. And so we can relate in some transform domain the hidden volume to the measurements through a 3D convolution. And so in terms of performance or compute requirements, this goes as n cubed log n, which is basically just restricted by how fast you can take a 3D Fourier transform. And we just need to store the hidden volume, so that's n cubed. And we can run this in less than a second on a laptop, and in fact we demoed a real-time version of this running on a GPU last year at SIGGRAPH as an E10. So this works really well. We have a few assumptions that we had to make to do this. We assume that the hidden volume is isotropically scattering, and it turns out we can also handle retroreflective objects. We also assume that we're imaging and illuminating the same point, so we have this confocal sampling. And we also assumed that the wall is planar, or we're scanning a flat surface. Let me show you a couple of results that we captured with this. So this is a mannequin that we captured. We put this around the corner and scanned the wall. These are the measurements that we captured. So these measurements you can think of as, again, like a trillion frame per second video of the light that's hitting the hidden object and reflecting back to the wall. And from these measurements, then we can apply this light cone transform and recover the hidden geometry. And here's, we did this as well with the exit sign. You can actually even read the lettering, see the arrow on the sign, again from around the corner, not directly viewing this. And compared to the other techniques, we can actually do much better, qualitatively at least. And we can also extend our model to account for things like sensor noise, incorporate additional priors on the reconstruction, and improve the reconstruction quality still. So this light cone transform model and image formation model I described is based on is a geometric model. And we had these assumptions that I described that go along with this. But it turns out we can also model this propagation of light from the wall to the hidden volume and back using the wave equation. We can have a wave-based model. And this has a few benefits. So we can solve this just as fast as we did before. And we don't have to make any explicit assumptions on the reflectance of the hidden object. So we don't have to assume that it's isotropically scattering. And we can also, it turns out, handle non-confocal samples and non-planar surfaces. So there are some nice benefits to this. And this problem of non-line of sight imaging in general turns out to be pretty similar to seismic imaging. In seismic imaging, they produce shock waves at the surface. usually using some sort of, well, sometimes they use dynamite to do this. And then those shock waves propagate down, reflect off of underground structures, and they pick up these pressure waves at the surface using geophons. And then the goal is to reconstruct this underground surface. Well, this turns out to be pretty similar to non-line of sight imaging. It turns out we can formulate our problem equivalently as not light scattering from the wall to the hidden volume or this hidden object and back, but actually light which starts from the hidden object at time 0 and propagates, or a wave that starts from the hidden object, the surface of the hidden object at time 0, propagates at half the speed of light to the wall, which we observe at, or we capture measurements there at, call it z equals 0. And so fundamentally this is basically a boundary value problem. We capture the value of this wave field at the wall at z equals 0, and we want to migrate it back in time to t equals 0 when it was at the surface of this hidden object. And we can actually solve this problem, we can solve this efficiently and readily. So first, before getting into the details on that, let me show you some results. So this was a scene that we captured on the left, and the measurements are on the right. And the measurements are interesting because they showcase a few of the different light transport effects that are going on. So these objects have different reflectances. The dragon is more glossy. We have this disco ball that's gives specular reflections, and you can see these effects in the measurements. So the bright dots are actually the specular reflections from the disco ball, and as it turns in the very front, you see these streaks from the dragon, which are more concentrated, and in the very back, you see these really broad streaks. These are best seen right at the side here. Farthest to the left, you see these really broad streaks coming from the statue. And we can play these back over time. This is the transient image. We would actually see this is the light, again, reflecting from the hidden volume back to the wall. So first you see reflections from the dragon, then the disco ball in the bookcase, and then finally there from the statue. And the goal is to go from these measurements back to the geometry of this hidden volume. And so I'll show just a few techniques, including our own, applied to these measurements. So this is a back projection-based technique. This is a proximate solution. This would also take hours to run on a compute node. This is the light cone transform. It has residual noise because it doesn't model these reflectance properties. And you can see that this technique called frequency wave number migration, or FK migration, which is this wave-based reconstruction, actually produces a much cleaner reconstruction without these artifacts. So how does this reconstruction work? I'll just give kind of a high-level overview of the math, and hopefully this will make sense. So here I'm just writing the wave field expressed as the inverse Fourier transform of the Fourier transform of the measurements. The Fourier transform of the measurements is there, and if you take the inverse Fourier transform of that, of course you get back the wave field. Now, there's this equation which we could find in our physics textbook. We could derive it from the wave equation, and this is just relating the temporal frequencies to spatial frequencies. So temporal frequencies f are related to the speed of light multiplied by the square root of the sum of the square spatial frequencies. And we can use this equation to perform a substitution of variables shown here, which relates these the Fourier transform of our measurements expressed. We can express the Fourier transform of our measurements purely as a function of these spatial frequencies, rather than having to have this temporal dependence. And doing this allows us to rewrite this top equation after the substitution of variables as the Fourier transform of the volume. So here, if I were to perform the substitution of variables, I set time equal to 0, and I take, this is just, then becomes an inverse Fourier transform, and I recover the this wave field at time equals 0, which is actually just the geometry. Well, here's a more intuitive view of what's happening. So we start with the measurements. We take the Fourier transform, And this is the measurement spectrum. But notice that we have it as a function of spatial variables and this temporal frequency. And if we do this substitution of variables, this is equivalent to basically stretching or interpolating our Fourier domain, our Fourier coefficients, shuffling things around. And it turns out that if we do this way, this is actually the Fourier transform of the hidden volume. So really this is just a Fourier transform, a resampling, and an inverse Fourier transform. And in this way we can recover the hidden volume. And this actually works quite well for even specular objects. So this is a simulation, but some specular bunny, these are the measurements that we would recover over time. And if we compare the reconstruction with FK migration to light-mode transform, we can actually do much better. We don't have these artifacts because the wave equation is much more robust to these even specular objects. Well, we built this hardware prototype to capture some additional measurements, and the main components here are a laser that shares an optical path, goes through a beam splitter, shares an optical path with our SPAD. This is just a single pixel SPAD. And then we have some scanning mirrors that allow us to scan where we're imaging and illuminating. And here's a video of the hardware prototype in action. So the laser is actually pretty powerful. This is about 1 watt average power. So you wouldn't want to be in front of this, but the diffuse reflection is icing. And so here's some additional results. We scanned just this dragon, and if we compare reconstruction with the light-mode transform to this wave-based model, we not only get better reconstruction quality, but actually it appears to be more robust to noise, even at lower exposure times as well. Here's another example scene with a bicycle that we captured. This is 10-minute exposure, and the reconstruction with FK migration is slightly better in this case than light-mode transform, and actually significantly better than the filtered back projection technique, which is more sensitive to noise. Okay, I think this is one of my favorite results. So we wanted to see how fast we can actually push this system. So we're scanning the wall at 4 Hertz, and this is me moving around in a retroreflective suit just to increase the amount of signal we have available. And we can actually run the reconstruction and see me walking around. We can see, again, just from the multiply scattered light, both where I am in 3D space and what I'm doing too. And finally, we captured this outdoor result that I showed earlier. And here's a long exposure photo, and you can just see the area that we scanned out on the wall. And on the right here are the measurements that we captured. And this is interesting because, well, since we're outdoors, you have ambient light, right? And so you see not only the indirect ripples of light splashing back from the hidden object, but also you see the wall that we're scanning itself. And this is from the sunlight, photons hitting the wall from the sun and being detected at the detector. And then here's the reconstruction again. And so actually this is fairly robust to that ambient light. We can still get pretty good reconstruction. So for a final topic, I just want to briefly go over some other work that we did on still non-line of sight imaging, but using sound. So in this case, instead of lasers and detectors, we have speakers and microphones. But the concept is pretty similar. We're going to emit sound from the speaker, and then from the echoes that we get back of the sound bouncing to the wall, within an object, and back to our microphone, we're going to try and reconstruct 3D geometry. Measurements that we capture are pretty similar. We get peaks from both the wall and from the hidden object. But in this case, we're not dealing with picoseconds. We're in milliseconds because the speed of sound is only 340 meters per second versus 300 million meters per second. And it turns out that we can still reconstruct the 3D geometry of these objects. Well, the high-level idea of why to do this with sound, or why it might be nice, is that since the wavelengths of sound are longer than light, the wall is actually much more mirror-like. So sound scatters off the wall specularly rather than the diffuse scattering that we have with the optical wavelengths. And so it should be easier to image hidden objects. Now, of course, we don't have the same lenses that we can use in objects to form an image from these measurements. So we have to apply different types of signal processing techniques. And it turns out we can use elements from radar image processing as well as seismic imaging again to do the reconstruction. So compared to optical non-line of sight imaging, where the signal decays as 1 over distance to the 4th power, because we have the scattering at the wall and then another scattering event at the hidden object, the specular scattering of acoustic non-line of sight imaging is much more forgiving. So it's 1 over distance squared. And of course, this is a lot less expensive. We can actually do this with off-the-shelf hardware components. So this hardware prototype I built, I actually just ordered all these components off of Amazon, with the exception of this translation stage. There are 16 speakers and microphones mounted on this vertical bar, and then it's scanned across with this translation stage. So here's a video of this scanning. So as it's scanned, we emit a transmit signal from each speaker, which is then recorded with all the microphones. And we do this sequentially and then scan it to each position. And here's a comparison of what we would get compared to an optical system. So this is a scene where we have just 2 cutout letters. This T shape is about 40 centimeters in front of the L letter. And the optical system, that difference is actually, that distance is actually really significant. So you can't really even make out the L shape. This was done with our previous hardware setup without the higher power laser. And in the acoustic setup, you can actually do this. And if you look at kind of the parameters of these experiments, we're actually about a meter further away from the wall in the acoustic setup. We can still make out both letters. And if you look at actually how much power you're emitting and how much energy you're using, we're further away and we're using 10 times less energy per acoustic transmission than we would use for each optical scan point with the laser. So it's just more signal efficient. And going forward, it might even make sense to think about ways to combine these 2 modalities. So, of course, you have LIDAR already on self-driving cars. Many cars, well, including, of course, self-driving cars, have ultrasonic transducers, like on your bumper, and even maybe a small array of a few elements of these transducers. And these could be complementary. So, for example, LIDAR has a hard time picking up dark objects, like the road or like tires, but if these objects are very solid or dense, you actually get a pretty good sound return from them. So there may be some merit in looking at sensor fusion in the non-line of sight imaging modality with these different types of imaging modalities. So just to conclude with a few thoughts, we can use these transient imaging data for a number of different applications. And this is a really emerging imaging modality that's been, I think, for me, an exciting thing to work on. So I talked a bit about using SPADs for 3D imaging and looking at the single-photon regime, a really low signal level where we're trying to push the envelope on either how fast we can image or finding ways to image at greater distances. And also, I talked about this emerging modality of non-line of sight imaging, and this is actually becoming a lot more practical. So I showed you some results where we did this outdoors. We're doing this at interactive rates, and so trying to push the frontier, making this more practical. And finally, talked a bit about doing non-line of sight imaging with sound. I think in general it's good to be open to these different imaging modalities and think about ways to combine these and improve the quality of our results. So finally, I'd just like to acknowledge collaborators. I worked with Ladlin and Intel on the acoustic non-line of sight imaging project last summer, and Matt O'Toole and Gordon Wetstein have been collaborators over the past few years, both at Stanford and CMU. And with that, I'll conclude, and thank you for listening.
there any questions?
Turn the link.
Oh.
I have one. So, question. The fact that you can extract the signal from noise and actually make sense of it is almost like dark magic.
Yeah.
Honestly. Amazing. How, especially in the outlights in the outside scene, how do you make the distinction? How do you extract the signal from the noise?
So the question is, how do you extract the signal from the noise, especially when you have lots of ambient light, right? So I guess I talked about, so in the non-line of sight imaging scenario, we didn't do anything explicit to try and subtract out the ambient light. The algorithm is just kind of robust to this, but to a point. So the outdoor results I showed were under sunlight, but it was during twilight. So what wasn't broad daylight, right? We tried it under broad daylight. There's just too much ambient light. In fact, you couldn't even see the signal, and without doing something extra, there was we didn't have a shot at reconstructing it with this particular algorithm.
Could you use specific laser, something either coded or somehow to subtract out just the ambient light?
Yeah. So could you modify your hardware, use laser, a coded illumination scheme, or some other technique to get rid of that ambient light, right? And of course you can. We had what we did in terms of hardware, we had a narrow bandpass filter, a narrow wavelength filter, so we were just looking at the laser wavelengths and trying to get rid of the other wavelengths which we weren't interested in, which come from ambient light. And there are other techniques. So like I talked about this Single-Photon 3D imaging project, in which we're basically using a neural network to try and censor out all the ambient detections and just detect, identify the photon detections from the laser. And that's basically what was happening. And there are other techniques to do this, analytical techniques where they'll they'll do some spatial pooling to try and average the signal and extract where those signal photons are coming. They're coherent, so if you average the signal together, you'll kind of see these peaks where the photons are, when the photons are arriving, emerging above the ambient noise floor. So there are certainly a number of computational techniques. We haven't looked into coded illumination schemes to do this, but that may be possible as well, certainly.
And another question, so the processing happens in real time as you scan, or are you capturing data and then post-processing afterwards?
Yeah. So is the processing happening live, or is the reconstruction happening live? For all these examples I showed, the reconstruction is happening after the fact. For the interactive example, though, the reconstruction running on a laptop takes around a second. It's pretty quick. We had this running actually with real-time reconstruction last year at SIGGRAPH, and that's just a matter of coding it up on the GPU and getting it to run. And that was with this light cone transform method that I talked about for the non-line of sight imaging. For the FK migration, actually that's parallelizable too, so you could do the same thing. And that could pretty readily run on a GPU in real time.
Going with the noise or ambient light issue, if every car on the road has these systems, is that going to be, or do you some sort of frequency hopping maybe to reduce interference, or what's the?
Right. So you put the LIDAR system on the road. Everyone has it. Are they interfering with each other? So this is actually, I've heard a few talks of people who are making these LIDAR systems in industry, and I've heard a few people say that they've solved this problem. And of course, they don't tell you exactly how. I haven't personally looked into this problem, but I suspect that it has something to do with coding the illumination and looking for that coded pattern in your return signal, or maybe they're doing something more clever. But people say that they've solved this somehow, but I don't know this.
So if they solved it, then you'd be able to, in a similar fashion, probably with your system.
Presumably, yeah, perhaps.
I'm sorry if my question is stupid, but your LiDAR has mechanical moving parts, right? There's galvanometer, and there is solid state radars. The phased array, is it applicable to your technology?
Yeah, so the question is well, we've been using mechanical scanning. Could you use phased array based LIDAR for this as well? And I think you can. You capture the same measurements. The systems I showed you were basically LIDAR systems. I can't think of any reason why you couldn't.
Would it increase the resolution?
Would it increase the resolution?
Yes.
Well, there's perhaps, maybe. So you may be able to, if you're using a phased array system, scan more quickly, right? And because of that, you may be able to scan more points. The trade-off is that if you're scanning more points, then your exposure time per point is typically lower, so you have less signal. But if that's permissible and you still have enough SNR, then yeah, you could scan more points, get higher resolution, perhaps with the phased array
So
scan.
it's more applicable for audio?
Is it more applicable for
Audio. You introduced two systems, right? One is
Oh,
wave
yes.
and now is audio. How do you
Could you use the phased array scanning for the audio system? You could, and actually that's one scanning technique. I used a different technique in this case, which made the reconstruction easier, and that was each speaker transmitted a signal independently. There's been some work actually in radar where they used a phased array to do through wall imaging, and they actually do the phased array and scan that way. Yeah. And actually, it's kind of a similar problem because you have the same sort of specular reflections at the radar wavelengths as you do for audio wavelengths. So I think the answer is yes, you can do it.
It seems counterintuitive that it would be faster to solve a 3D partial differential wave equation than to solve the convolution. Do you have any theory why it's faster and why it's more accurate?
So why is the wave equation solver faster than this Lycone transform that I talked about? So it's actually not faster, it's the same computational complexity. And it's because both methods are limited by the 3D Fourier transform. So this Lycone transform method basically had an interpolation step that brought you into this transform domain where it was a convolution. And to do the deconvolution, you have a Fourier transform, a division in this frequency space, and then an inverse Fourier transform. And so that's how that works. In the frequency wave number migration, you have a Fourier transform, then an interpolation, then an inverse Fourier transform. And so it just actually turns out to be the Fourier transform that limits both of these.
Why is it more accurate for the wave equation? I guess because it takes well, it's more than just one direction, right? It's not confocal.
So why is the wave equation method more accurate? It turns out, so it works better on the complex reflectances because we're not making explicit assumptions about the types of measurements we get. So for this Lycone transform method, we assume that the measurements have a kind of fixed point spread function that they cause. Well, that point spread function, or that blur kernel, will actually change, and change significantly depending on what types of reflectance you have. So actually, this is the difference between those bright dots that you get from the disco ball and the big streaks that you get from like the statue, right? And the Lycone transform treats both of those the same. The wave equation presumably can handle these different VRDFs, or at least implicitly. And in practice, we observe that this is more robust back to it. And there's also some evidence that the wave equation operator is actually the adjoint rather than an inverse operator. So typically, amplify at high frequencies like an inverse operator that we use in the Lycone transform.
Is that why the light cone transform of the bicycle, you saw kind of this boundary edge on the bike and very planar compared to the other? Is that related to that issue then, or?
Yeah, we think that those artifacts just occur because it tends to amplify the noise more. And just empirically, we're certain that the wave model is more robust, perhaps because of these mathematical properties.
Could you say some more about the neural network that you use for? What is it taking the images and the depth?
Oh yeah.
And
Can you bring the topology of this network?
Yeah.
Yeah, what's your data training set over?
Yeah. Okay. So more details on the neural network for the 3D imaging. So I didn't spend too much time on this because I wanted to get to non-line of sight imaging. But okay, so let me talk a bit about. Oh, let me switch this. Okay, so the network takes as input the SPAD measurements, and this is a 3D volume. And then the structure is, well, I built it after looking at some segmentation, networks that are used for image segmentation, because they were basically trying to solve a similar problem, which was kind of a per pixel classification. Here we're trying to classify when the Single-Photon arrived, and in image segmentation you are identifying each pixel to be one of a certain class. Well, here we have these kind of bin indices as where the photon could arrive, and those are kind of like classes, right? So I came up with this multi-scale architecture that was similar to these image segmentation architectures. So the SPAD measurements come as input and are downsampled in this branch. We have a number of 3D convolutions that are used to process it, and then you can also pass in features from the intensity image in the middle of the network. So fusing things in the middle, and then you have a few refinement layers. And the network basically does just that. It tries to classify the bin where the photon, or the laser photons arrived at. And then based on that, you can estimate the depth map. And we trained it on, did you have a question?
Your ground truth is a point cloud?
Yeah.
Yeah, so the ground truth is, so we trained this on the NYU V2 data set. This is a data set of RGBD images captured with a Kinect sensor. So we took these RGBD images and then simulated SPAD measurements. And then the ground truth was basically these bin indices corresponding to the depth. And then and then we trained based on that. So it was trained on simulated data, but then we also evaluated on some of the captured data to make sure that we could actually transfer that learning. Yeah, I think if you have the resources and the time, you can always get better performance capturing a data set with your actual physical hardware going on.
Did you do any data augmentation?
Augmentation?
Yes. Did you transform anything? Did you jitter it?
I think we did some like random cropping and shifting, during the training. And we've been working on this since then, trying to make this better performance, run faster. This wasn't running at real-time rates because the volumes are so large. So this is also still ongoing work in the lab.
I know you're doing more depth, but how does your denoising compare to like what other companies are doing for like ray tracing or other domains? Is there significant difference between that?
Okay, so differences compared to like ray tracing, denoising.
Yeah, or camera. Anyway, just curious if there's whether they're very similar in terms of.
I think the models are quite different for. I'm actually not too familiar with the ray tracing denoisers and what they're doing there. If it's they render out the image and then they pass that into a network that denoises it, which would be a straightforward thing to do, and that's more like just a 2D image denoising 2D images. This was a little different in that we had these kind of more like a classification problem where the network's kind of implicitly getting rid of the ambient detections and then trying to pick out where the signal is.
But there's still sharp edges and stuff on objects, right? That are that So I mean, there is that kind of, you have a significant color change or something that might occur on
Yeah, so presumably the network is picking up on all these gradients in the intensity image and using that to identify perhaps which areas in the SPAD measurements it can average together to try and extract a meaningful signal. So that could certainly be going on.
What kind of material limitations are there? Like, for example, water or smoke,
So for just in general, or
just in general.
okay, so what types of materials can we image?
Right.
Right. So I think for water or fog or something like that, you're breaking a fundamental assumption of like a depth map, right? Where each pixel there's a single depth, or like if you have translucent objects or something like that. If you're primarily interested in imaging those objects, I think you have to take a separate route, or have some other model where you can maybe have multiple, you can account for multiple layers of depth. And we don't explicitly do that here. And we don't do that. Well, if you look at doing this in the non-line of sight imaging, we certainly had objects at different depths, and they could even include each other slightly in the reconstruction. So that kind of implicitly accounted for that case, kind of, but again, we're not looking at like fog or water. I think that is a more challenging case.
You did work with both single-chapter GMAPDs and linear-arrays GMAPDs, which in my experience have neighboring avalanche issues. I was wondering if you dealt with those or if you had different quality of reconstructions from the single-sector versus linear array.
The question is, what was the difference between the single pixel SPADs and the SPAD arrays?
Yeah.
And how do they compare? The single pixel SPAD is actually a lot easier to work with. The line array had worse temporal resolution and a lot more noise. So these SPAD sensors have a dark count rate, and these are just false detections, basically. And the rate for the SPAD array that we had was somewhere in the thousands per second, and for the single pixel it was 40. So it's a big difference in the quality. Also, the single pixel was a lot larger, so we got more light. But this is the SPAD array we had was already a few years old, so I think they've improved on things like fill factor and resolution and things like that. So you may be able to do better now.
So Elon Musk said there's no need for LIDAR in self-driving cars. So where do you think this will solve that like cameras don't solve?
So how do you respond to Elon Musk?
Yeah.
Well, I think he has a point that you can do a lot with stereo cameras, and they've shown that, in fact, their autopilot system seems to do fairly well. I mean, with some exceptions, right? With just using the cameras.
No, it's fusion. There is radar too. It's fusion of sensors. There is no LIDAR, but there is other sensors, not just cameras.
Cameras, radar, they have ultrasonics as well. Right, that's true. There are challenges with using stereo cameras. Maybe the radar helps alleviate this. I mean, if you have a textureless region, right, that you can't tell what it is, I mean, it's going to be pretty hard to estimate depth there. Just using stereo matching, maybe the radar helps with this. LIDAR would help you get to better depth resolution. Ultimately, and I think one of his arguments is that LIDAR is just too expensive, and you can't put it on the car right now and sell the car for a reasonable price. I think in the coming years, we're going to see the prices drop. As these LIDAR modules are mass manufactured, and if it's cheap enough, why wouldn't you? And it makes the vehicle safer. Why wouldn't you put it on? I think so. I think maybe in a few years when these are cheaper, maybe things will shift. Right now, they may be too expensive to put on a consumer car that can be self-driving.
It seemed like when I heard that basically the problem right now with some of the sensors is they aren't fine enough resolution actually and responsive enough in order to deal with highway speeds or such. And I guess this is dealing more with urban driving probably as opposed to, is there any application you think in that respect in terms of longer range or higher precision scanning, or, you know, like a fovea type view or something maybe if you...
So, yeah, what are the main challenges in a scenario where you're on the road and are the current sensors accurate enough or quick enough? So the sensors are actually pretty accurate right now. We have a Velodyne in the lab that I've played with a little bit, and they say that you can get to a couple centimeter resolution at over 100 meters. That's, I think, pretty good. You need to be able to, well, from what I've heard, you need to be able to image a couple 100 meters out at least if you're at highway speeds, and that's still, I think, challenging. One, because the point cloud is actually pretty sparse at the distance, and then two, because you don't get signal back from some areas. This line of work, I think, is helpful because it shows that you can apply a bit more, maybe more cleverness on the computational algorithms, on the reconstruction, and this may allow you to push out that distance further, or maybe allow you to scan faster because you can handle a lower SNR, and then that may help with these problems of the point clouds being sparse or the range being limited. So I think it's an ongoing effort to address those concerns, and they are concerns.
So is that to say that you have applications in direct line of sight for like the denoising side of it? Is that what you're just talking about? As opposed to, I was trying to think of the practical application of the reflected hidden things, say in a moving vehicle or something.
Yeah.
Have you looked at, considered that?
Yeah, so practical applications of the non-line of sight imaging stuff. I think the big vision is to, could we put this thing on a car and have it kind of fill in the 3D point cloud for, detecting maybe there's a car coming around a blind turn or something like that. That would be the big vision. We're not quite there yet. I think this recent work goes more in that direction. We showed you can take it outside, you can do this faster. Of course, the laser that we have is an eye safe. We probably need to move into like a long wave IR, where you can boost up the power and still be eye safe. So that's still ongoing work. Making this practical is a pretty big challenge. Did that answer your question?
Yeah, I think so. I mean, the other thing is, it sounds like, right now for your testing equipment, you're using a very specific setup and more powerful lasers. Do you see that being doable on, say, the Velodyne LIDAR that you're looking at? Could you do that with an off-the-shelf device, or are you not getting the data back because you only get the unified point cloud of the first thing that it sees?
Yeah, so can you use existing systems to do this? We played around with this Velodyne LIDAR for a while, but the challenge was that we didn't have access to the raw data, which we really needed. So they primarily give you just the first return. There's a dual return mode, which I think is typically for a situation in which you have maybe like a glass or something. Yeah, you can get that second return. But for us, it wasn't really, we wanted the raw data. We haven't been able to get that yet. But if you know of...
I was going to say, Velodyne's not very far away, so you probably could...
yeah, so if you can convince them to give us the raw data. Yeah. Yes.
Our next talk is on simulation driving. Have you looked at perhaps trying to provide a model of what this could do for some of these open source simulators so they could kind of evaluate, the practicality or usefulness of that?
So, yeah, perhaps extending open source simulators to, and I think some of these will give you like a point cloud like you would get from a LIDAR, which would be the first return, but also giving, if you could extend those to the second return and more.
Or perhaps some of this, bounce or even, or, extra data, how much does that help in terms of driving?
Yeah. Well, I think, you could certainly do that. We haven't looked at this yet. I think it's a good idea.
It might be easier to model what you would want out of something like a Velodyne because you can actually do that in simulation and then give that result to the software developers upstream and say, what if you had this information?
Yeah, I think it's a great idea. And simulating the raw data, and that's probably what you'd want to do, especially for us as we get closer to putting this on a car and then trying to demonstrate some of these things, I think, yeah, we definitely keep that in mind.
The hard part about that is you'd have to raycast for all of that data, and most of the simulators are actually not doing that for performance reasons now. So they're doing, depth camera tricks instead for performance, and that makes it sort of impossible to get the data in real time anyway. I mean, you can certainly do it on real time.
Yeah, I think that makes sense.
So, if I understand correctly, this non-line of sight technology, any plane object becomes a mirror, right? So that's great, that's awesome. But that's if you have information that this object is plane, if you already have prior knowledge about this object. If you are on the road, maybe you don't know about objects if they're plane or not. Is it possible to compute it on the fly and deal with a non-plane object, like car shape? So, I mean, it's great, it's awesome. Your technology is basically saying that you will fill up all the gaps that LiDAR has right now.
Yeah. So the question is about the scanning geometry. Could you do it on the fly, handle non-planar surfaces? See if I extra slide on this. Oh yeah. Okay. So we did some experiments on non-planar surfaces. Okay. So I had this projector screen that I deformed, so it wasn't exactly planar. And well, you basically get the 3D geometry for free because you're scanning the surface and you get both the direct and the indirect light, right? So you can get the 3D geometry and then you can use that to inform the reconstruction. So we scanned this 3D surface, we had a couple of cutout letters again, and then if you just ran the reconstruction on that data, of course you don't really get anything. If you can actually apply a phase correction based on this 3D surface and then run the reconstruction, in that case it actually works. So if you have that 3D geometry, you can incorporate that into the reconstruction to make it better. Now, of course, this is kind of a simple case where you don't have like multiple interreflections, even higher order bounces, but in theory, maybe that's practical. Yeah.
You had a bunch of artifacts on the bounce acoustic version.
Yeah.
Did you scan that without the bounce? I mean, are those perhaps artifacts in how you constructed those things so they may look that way in the acoustic domain?
Okay, so artifacts. Oh yeah, artifacts in the acoustic reconstruction. Yeah, so.
Yeah, did you ever scan those without the bounce then? Or those non-bounce ones?
You'd still get it if you weren't bouncing it, actually.
Okay.
So I think what you're talking about are these kind of gaps in the letters, right? Or,
Yeah, there may be, where
Yeah.
things are connected, it may
Exactly.
just resonate or something at different spots.
That's what we think is happening.
Okay.
So we think that at these, I actually had two boards that I put together, right? And there's this seam, and you see a dark patch there. And I think the sound's actually being diffracted around there rather than reflected back.
Okay.
And so, yeah, you're in this acoustic modality, and so things don't look quite like you would see them optically. But yeah, that's right. Okay.
Elementary question. So how did you start overcoming the reflection limitations? Where at one point you were saying that, okay, now we can do reflective surfaces.
Oh.
So what was the is it just a different scheme, or is it like a change of tools? What helped you overcome that?
So, yeah, so how can you reconstruct the reflective surfaces better? So I think it was this shift from a model that was purely geometrically based, where we assumed that from this hidden object, light would reflect in all directions back to the wall, to a more sophisticated model that was based on actually the wave propagation and this idea of migrating the wavefront that we observe on the wall back to the surface of this hidden object without making explicit assumptions about light had to reflect from that hidden object in all directions. And in fact, you could have different BRDFs of that hidden object, and if you migrate that wave front back, then it still comes back to the surface of the object, kind of regardless of how it was emitted. Or at least that's what we've observed with this reconstruction method in practice, is that it's pretty robust, like to the disco ball.
Right, okay. So basically just the way you interpret the information is what changed.
Yeah, I think implicit in these models is underlying assumption about the light transport, and we're just not making these explicit assumptions about, you have to have an isotropic BRDF in the wave-based model, and so it's more robust to different BRDFs.
I think we're just about out of time. I'd like to give an applause to and you could probably ask some more questions while we're packing up.
Yeah, thanks you guys.